All right, thank you everyone for being here. I'm Cedric Honnet, I work at the IRIT Lab. Today we're receiving the visit of Christophe Jouffrais, who's going to present his work between accessibility and HCI. I'm not going to give much more details. I think you can start from now.
I can introduce myself quickly.
Thank you very much.
Thank you for inviting. Thank you for coming. So yeah, I'm a CNRS researcher, currently working in Singapore, but my main lab is Toulouse, IRIT. It's the place where I've done all this work. I'm gonna talk quickly about Cherchons pour voir. This is a common lab that I created between the Institut des Jeunes Aveugles, the blind Institute for Young Blinds in Toulouse. We're working together on many projects. And then I'll show you mainly two projects that we have done recently on tangible interactions for blind people, accessibility of maps, related to accessibility of maps. And if we have time, I can talk a bit more about different things. So what is Cherchons pour voir? So this is the a collaboration between IRIT, Institut de Recherche en Informatique de Toulouse, and Institut des Jeunes Aveugles. IRIT is a big lab. We are 700 people working on different themes of computer science, and one is interaction. And we identify four main application domains, and one is health and autonomy. This is the axis that I'm leading. So there are many people involved in this axis, coming from network, image, and so on, and people from interaction. And on the other side, this is this Institute for Blind People, IJA. So there are about 120 people working there from different training, so orientation and mobility trainers, psychologists, doctors, medical doctors, etc. So we can work with any of them. And we created this common lab. The idea behind that lab is to work together without being shaped by subvention, by projects, by getting some funding from the INR. So we can work every day, all over the year with them. And we identified different missions. So first we work together on what are the needs of the specialized teachers in the institutes, the trainers and so on, the needs of the visually impaired people. And we do both more fundamental research, but also applied research. You'll see that later on. So there's a website now. So recently we have been working on mainly mental representation of space in blind people, and the two maps project that I'll show afterwards are dealing with mental representation of space. But we have been working on tactile code too, auditory code, and of course non-visual interaction. And we have many different little projects. So I'm going to talk about this one and another one that is not presented. So maps are everywhere. Of course, you know that, with many different purposes. Of course, you know maps are mainly visual, so it's quite a challenge to provide accessibility to maps for visually impaired people. And this is the challenge that we want to address. This is a map, just a screen copy of a map from Google, and you can see many things. So the different countries, the different cities in the countries, you can put little stickers on that and select points and select itineraries between points. You can do many things. But when you are blind, then you have to adapt that, because if you just translate that into something that is tactile, there is much more, too much information. So the adaptation is that process that is made by a tactile document specialist. That's a person that is trained to that. And you can see that they remove a lot of information in the map, and they simplify the different outlines. So everything must be simplified to get accessible by touch. And there are only maximum 7 different elements on the tactile maps. So it's really limited. There are many projects. It's now, I would say, 30 to 40 years that people are working on accessible maps, and there are many different projects. These are quite old projects, but that still make sense. This one is a physical representation of the campus, and that is interactive, so you can press different parts of the physical representation, and then you receive audio feedback. And this is really useful, of course. It works. It's very convenient. And this was a bit more recent. You can use this relief map. So this is a special paper. Everything that is black, the spray printed in black, when the paper is heated, it gets in relief. In fact, it expands. So you can feed it with the and then what they did, they put a tactile screen under the map, so that when you explore the relief map, then you can press different parts of the map and get audio feedback. And this works too, of course. But then you can see that nothing is dynamic and not change anything on this map. Where everything is designed, and then you can access the map, but you can't do anything that is not prepared. So the challenge that we had is to provide access to dynamic maps. How can we do that? Just before that, a few words about that device that we designed during the doctoral work of Henri Brock under my supervision. So this is a replication of the prototype I showed before. This is a relief map that we put on a tactile screen, and we designed many different interaction menus so that you can access different layers of information on these tactile maps. The children are able to play with that. And then you can add many different functions on that device, select different parts of the maps, compute itineraries, put sounds, etc. So the teachers, they get one software to build this map, and they have many different use cases that are very interesting. One is, for instance, an orientation and mobility trainer. We'll see that a bit more later. But is working with blind children outside. So he brings children in the street, and then they are talking about space, but they also record sounds on the different places that they visit. So for instance, they can throw a stone from a bridge, and they record the sound of the stone falling in the river. They can go to a crossing and record the crossing, etc., etc. And then when the teachers come back to the school, he builds its own map of the neighborhood, and he adds the sound on the maps that he recorded with the children. And this makes sense because now the children is able to make the link between what he experienced outside and what he's working on with the map. So this is very nice device that we put now in the different classrooms in the institute. So French teacher use it, English teachers, math teacher, geography teacher, orientation mobility trainer, everybody is using it. Yeah, one point that was very exciting is that most of the people working with blind people, they say that you shouldn't lose time to train them to understand space as an allocentric representation. So what is very useful for blind people, they say, is providing them with different, a series of procedures. So if you want to go from the institute to, let's say, the metro, then you go to the door, you go straight for, I don't know, 20 meters, then you turn left, you got the exit of the university, then you cross the street, then you go a bit right, you go to the metro station Jussieu, and this is, for them, much more reliable than training them to explore a map that would be a map, an allocentric map of this neighborhood.
Nobody can use them anymore.
the maps
here. Yeah.
Yeah, but you know that yeah, but what is interesting with maps is that imagine that now you are work roads. You have something that prevents you from crossing this entrance. If you only have procedures to get out,
just go around.
You're stuck. No, you don't know how to deal with that. So maps are very important because you can compute alternative ways to go, and you can make many computation about the distances between different points and so on, which you cannot make when you only work with procedures, with egocentric procedures. So this is very important to get map representation in mind, not just only procedures. And they used to say that for them it's very useful to get procedures, and they don't want to waste time about maps. And I didn't agree with that, because you can make so many different operations.
It depends on the place.
Yeah, of course. Probably it depends on the place.
And this campus is particularly interesting for that.
Because it's too complicated.
As an architectural statement, to make it like a map. You know, because
this is a challenge we could address.
And it completely failed.
So you try to learn that.
Yeah, nobody understands the logic of the towers and the connections. It's supposed to be a map. Yeah.
Could have a look at it.
Yeah.
So anyway, we checked that. We checked that. I mean, they told us that in addition to that, blind people, because they are not used to mentally manipulate maps, they are not very keen on doing that, and they fail. Yeah. And we checked that. We checked 3 different information about space: the memory of landmarks, the different landmarks that were on the maps, the memory of the route to go from one point to another. So there were many questions that we asked them about routes, and survey representation. So let's say compute the distance without going through routes between 2 points of the map, and the relation between these 2 points. Is it north, is it west, etc., etc., etc. So we were expecting that they would fail on the survey representation and they would succeed in the route representation, according to what people think, the profession, the teacher, they think. What we observed is that, of course, they are very good with landmark memory. This is these orange points here, almost perfect. They are very good, still orange, with route. It's the score is 9/12, and they are very good on survey representation too. It's almost the same score. 9, 9.
How do you compute the score?
So there are many questions that we ask them about the maps. So a series of questions about route, a series of questions about survey representation, and then we just compute the score. So that was first a surprise, because they are as good with survey questions that with route questions. But then we called them back 2 weeks later without, they were not, they didn't know about that. We called them and we asked a series of questions again. And what we observed that, of course, they forgot a lot of landmarks. This is the blue bar. Not surprising. Everybody would forget about the names of the landmarks. They forget a lot about route, 21% of drop down. And what is less forgotten is survey representation. It's only 13% drop. So not only they are good at manipulating mentally the survey representation, but they are more robust in time. So that was a very interesting result that we got with this.
You made confidence?
The confidence is, we were just asking them how sure they are about the answers they give. So on a scale of...
yeah, because there's a lot of research in confidence now at the theoretical level, as a proxy for the ability to think of a cognitive topic. rather than raw performance.
So
that's
this is we are not very confident about this method because we only ask.
So the dogma is that actually confidence reflects performance.
Yeah.
And so my question is, does it
perfectly
the case?
You can see that it's perfectly the case, except here.
So
where there is a difference.
You don't need to measure performance. You have to do it as confidence.
Yeah, but we were surprised too because when they declare, I mean, you ask them about survey representation. Even the blind people that participated to the study, they say, no, I'm not really confident about manipulating maps. I'm not used to that. But anyway, if you ask them, okay, you get this answer, this answer, this answer, how sure are you about the answer that you get?
The interesting case is when confidence doesn't track performance.
Yeah.
That's where it's interesting.
Probably.
Because normally it does.
Yeah, normally it does.
But there's another interesting counterexample.
Yeah.
So you have never...
No. We have not worked on that. That was a very simple measure just to know what's going on if themselves were, I mean, confident about the answers they gave, but we didn't pursue in that direction. So it was just a trivial index. Trivial measure.
You measure the confidence and the accuracy?
Yeah.
The diagram shows
we have 2 scores.
Okay.
The orange one are just after map exploration, and the blue one 2 weeks later. And we measured both confidence and the scores.
Just a question.
Yeah.
I have the impression that there's a difference between what orientation and mobility trainers said and researchers, because I have the impression that researchers used to say that blind persons have worse performance concerning allocentric representations than sighted, but they are not unable to do them. I mean, they do have an allocentric representation.
Yeah, they're able to.
It's less good than sighted.
It's less good for me because they don't train it.
Yeah.
That's the only point for me. It's education, it's expertise, it's the number of times they get access to maps. And this is not a mental process, this is not a cognitive process, it's just how frequent are they facing maps. That's, for me, that's the only point. Probably the young blind people, they need time to understand space, the survey representation of space, but then there is no difference. We'll see later that one of the best subjects that we had in manipulating mentally a different level of maps with different zoom levels and so on was an early blind.
No, yeah, I totally agree with that. Well, I think that maybe blind persons would have to train more than sighted, given that vision is simultaneous, whereas audition and touch are
sequential. Yeah.
Yes, but with a proper amount of training, there's
That's the message I try to transfer in the center. I mean, they are not reluctant about that, and they are they agree. But they used to work on procedures and less on maps. And this is, for me, this is an error. I mean, even if the procedures, if going from A to B is very important, they should spend time talking about maps and exploring maps and so on. That's the point. So it's now 3 years, 3 or a bit more, something like that we are working on that project at Assistive Technologies. Gilles is working with us on that. So as I said before, one of the objectives of the project was providing accessibility. I didn't measure the time, so someone has to tell me when it's too long. So, how can we make something dynamics on these maps? So one of the research that we did, and Gilles and Emeline were the leaders on that, was using small objects that are recognized by the map, the tactile screen, and they can manipulate the different objects and provide interaction to these objects, which was very interesting. So now, more than just having a map with the outlines of a neighborhood, you can add a bridge, you can add a small bridge, a big bridge. So this is the bridge for the train, this is the bridge for the people, And this is the place where they recorded the sound about throwing the stone. So the teacher has been working on this setup for a while with different children. We designed, as I told you, different softwares. One is to draw the map and the interactions of the map. And the other one is just the player that you can use on your Android or iPad tablet. And now we are working with another company that is making maps, put them on the market. So this is the same kind of map that can be used for building. And then the blind people, they can go to the desk and ask for a mobile one, and they can move with it. So the content between the two maps are a bit corresponding, but on this one, they receive more guidance cues. So this is... Does
it have any dynamism?
No, this one is still static. Yeah. They put a patent on this little thing because it's very easy to change the map.
Yeah.
So we can replace it.
You could have vibrations depending on where you're...
No, it's just audio feedback. Yeah, on this one. But probably we'll put vibrations and another. We were talking yesterday about deforming the map with heat. So we have many ideas to improve that. More than that, I told you that we want to make it more dynamic, and now we are coming to that. So we thought about, and this is the work of Julie Ducasse, her doctoral work. We were thinking about, okay, we want to get rid of the people that transcribe the map from the visual map to the tactile map. We don't want anybody to draw the content, to have the interaction, etc. We would the ideal scenario would be the blind people is approaching the screen, tactile screen, and you can have access to the data. And this is one of the systems that we designed. So this is a little circle with a code. I'll show you under the circle. And there is a guidance. So first step, you put one circle on the tactile screen. Then you can link different circles. You put them at the right distance, and then there is a guidance for the second circle, and so on and so on. And you can draw your own map. I'll show you a small demo.
We introduce a new tangible tabletop interface that enables visually impaired users to independently construct and explore tangible maps.
So all the videos are with the blind people. There's no sighted people playing with it.
Our approach can also be used to construct and explore other types of graphical representations, such as bar charts, organograms, and geometric shapes.
To my knowledge, there was no music at that movie. This is strange.
To do so, we designed an original type of physical icon called tangible reels. It is composed of a retractable reel that is used to make lines tangible. To ensure its stability while the user explores the map, the reel is either glued on top of a sucker pad or on top of an object filled with lead. A pre-study showed that sucker pads are more stable than weights, and that the tangible reels are easy to move on the tabletop and to manipulate. Participants also had to explore and memorize several maps built with tangible reels and to draw them. Results showed that the participants were able to understand the maps. Tangible reels
I know why.
only slightly.
I was listening to music in the plane. How is music anyway?
The user progressively constructs the map by following audio instructions that indicate which tangible reels must be attached together and where to place them.
Ligne de tracé. Attacher un objet vers le bas. Attacher. Bas. Bas. Droite. 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 Être monté. Ligne 3 tracé.
A two-step guidance allows the users to quickly move to the target before following more precise and frequent instructions.
À droite. 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 D'y trouver. Ligne 7 tracé.
Audio feedback is also provided when a tag is not detected, for example, when it is hidden by a user's finger. The user can also explore the map and retrieve the name of the points and lines.
Ligne 5. Ligne 6. 7.
We evaluated our system with 8 visually impaired users. They had to construct 4 maps of increasing complexity with the sucker pads and explore the maps to find the name of the start and end points of 3 lines. 27 maps out of 32 were perfectly reconstructed. Participants found the instructions clear and easy to understand. Completion times to construct the maps varied from 2 to 4 minutes. On average, participants spent less than 3 seconds in the rough guidance phase, which allowed them to place a tangible reel in the right place in only 24 seconds. The time to answer the questions increased with the complexity of the map. Overall, 90% of the participants' answers to the exploration questions were correct. Participants agreed that constructing the maps was not demanding and were highly satisfied with their performance. Our interface and our tangible reels allow visually impaired users to construct and explore maps without assistance.
Okay. So,
The data is on how many participants?
The
data, sorry, it's on how many participants?
it depends on the step, but I don't want to say something wrong. Around 10 probably each time. Yeah, something like that. Yeah. Okay, so this was really first a success. It's very surprising. It works very well. The blind people, they like it, and they can draw many different things, many different kind of graphs. So of course, this is a lab prototype. So we were thinking about how to transfer that to the Institut des Jeunes Aveugles. And finally, we designed something simpler and cheaper, very cheap. So our goal was to get something that is, let's say, less than 50 euros or something like that. And we came out with this device that we are starting to use in the Institut des Jeunes Aveugles. So this is a box. The principle is exactly the same. This is a box, metallic box, and inside we put a raspberry with a webcam. And under each little element on the map, so the different things that you can put on the map, there is code, and the camera is looking at the code. So we know at each time where is the object on the map. And then you can provide interactions or guidance to manipulate the different elements of the maps and work about anything that you can imagine. So this was an exercise for 6 to 8 years old blind children, and they learn how to deal with time. So we have different representation of time, and we must put the correct time, or learn about English time and so on. And we have made many different exercises with that box. And the last one is a collaborative game. So we have been working with how do you say, editor, an editor de jeu. I mean, this is a commercial game you can buy. This is the Chaperon Rouge. So you have to work with everybody. So all the players have to work together to be faster than the wolf. If the wolf is faster than the Chaperon Rouge, then you lose. So we have to talk about which decision to take. So we have to explore the different elements on the tactile setup. So we have many different places where we have to take information about, I don't know, the number of steps, and so on and so on. Where is the wolf, and so on. And we presented this game at the Festival International du Jeu 2 weeks ago, and it was very nice. So finally, we got support from Altran, Fondation Altran, and they're gonna help us to make something that we can put everywhere in France, but in the world too. So it was very, very interesting too. Last project that I want to talk about, I'm still okay with that, because of course with that previous project, so now the user is able to draw and explore his own map. So he doesn't need anybody to build the map and play with it. But I'm talking about maps, but you understand that it's much more than maps now, because you can have access to graphics, to drawings, to anything that you can imagine, games. But last part of the project was, can we make something dynamic in terms of different viewpoints and different zoom levels? So can the map adapt itself? So we were, of course, looking for little robots that were able to move. So once they are at a good position, then you can change, imagine the zoom, and then the robots that just go themselves to the accurate position.
But map enables visually impaired users to explore tangible and dynamic maps. Landmarks are represented by robots that move to their correct position whenever the map is updated. Users can interact with them to retrieve their name.
Johannesburg, Nairobi, Cairo.
We designed 2 interfaces that enable users to center a landmark, zoom and pan.
Dakar.
Here, the user is centering the viewport on Dakar before zooming in. Users can switch between 3 zoom levels to display more or less details. For example, in this video, the 3 zoom levels are metropolises, cities and towns. Users can also pan the viewport over the map to explore it. The keyboard interface supports discrete control. When panning, users can move the viewboard using step-by-step movements. Feedback concerning the position of the viewboard on the map is given accordingly, using clock face directions.
12 o'clock, 3000s, 12 o'clock, 6, 12 o'clock, 9, 12 o'clock, 6, 12 o'clock, 3.
When zooming, users can select 3 predefined scales, 1 per zoom level.
Metropolises, cities, towns, cities.
The sliders interface supports continuous control. When panning, the viewboard can be moved in any direction and distance. Feedback concerning the position of the viewport is given every 2 seconds.
12 o'clock, 9, 12 o'clock, 6.
When zooming, any scale can be selected. We conducted 3 user studies. Results show that the 2 interfaces enable users to not only explore pan and zoom maps,
So what is important here, once again, after discussing with many teachers, they told us that Zoom, concept of Zoom, is really a problem for blind people because they are not used to Zoom. So one of the questions that we wanted to address is, are they able to manipulate Zoom mentally? So during our design sessions, we were very cautious about the fact that it makes sense when you zoom. So there was always at least one point that was on the previous screen that still was on the screen, the following screen, so that there is always one reference point, so you can understand what happens to the screen. So we checked that during the design, so it was working, and then the question was, okay, there is condition in the experiment where there is no way for the blind people to see the whole setup, all the points that were on the map. So they had to mentally acquire one little portion of the map, then maybe they move, they acquire a little portion of the map, and so on and so on. So they have to mentally integrate all these different portions of the map to get the whole picture. No way to do that differently.
What was the task?
They were asked to move from one point to the other, then to find the different, let's say, village that were around this main city, and then they were asked to find another city somewhere else and find, and so on and so on, and then to move very far away to do something else, come back, and so on. So they have seen, yeah, they have seen the whole map, but never at the same time. And the question was, okay, now are they able to relate this point and this point that they didn't see together? Okay, it's quite complicated.
For non-blind people, it is for sure. I don't know.
Okay, let's see the result.
To understand them. We also gathered feedback on the use of robots for non-visual actuated tangible interfaces, as well as on navigation aids.
Okay, so this is the Standdown NASA TLX test. So we can see that, of course, it's a very difficult task for them. The mental demand is very high. This is not a surprise. It's very difficult, even for sighted people. It's very difficult. So the effort is quite high. Frustration is quite low. Good. We designed something that is usable, at least not bad. And on the temporal, because the robots, they need at least 3 to 6 seconds to move from one point to the other. But this is not frustrating for them. It's okay. They're okay with that. It's not a problem. We had two different interfaces. One is you press the keys of the keyboard to zoom and move the map. And there are our hypothesis that they are much more used to that because they do that, always do that with the word processor and so on. And the other one, the sliders, were the robots that we used to move. And our hypothesis that was that they should be less confident with that, because they are not used to that. But the difference between them is not that big, in fact. It's a matter of preference and things like that. So what about the maps now? This is a measure that we used to check that the maps that they draw are good or not. So we asked them to reconstruct the map. So they put points. So we get them a surface that is the same size that the one they explore, and we asked them to put the points. So we put, I guess, 2 first points that serve as a reference, and then they had to put all the other points on the map. And then we measure the distance between the correct position of the points and the one that they chose. And you can see here this difference. So this red line is the distance between the real position of the map element and the one that was set by the user. So this user is very bad. Okay, you can see the correlation between the real map and the reconstruct map is 0.2. This is very bad. And this user is very good, 0.95. And these are all the users that we got during the study with the two different interfaces, keyboard or sliders. So first you can see that they are good as a majority. Only 2 users are bad, let's say, or the other one are more than 0.5, which means that they are better than the average. And now, who are they? So this is not a study that allows to telling that this is the truth, but just a few examples. This guy has residual vision, you can see, and he sometimes uses his residual vision to behave. This one, he got blind at 30 years old. So he's a late blind, very late blind. This one is 60 years old, but he got blind before the age of 3. And he's the best one. Okay? So I was telling you before that for me, the point is that they have to play with map. It's not because they are late or early blind that makes the difference. The difference is, are they playing with map? Are they accessing map? This guy he loves maps. He go walking every day. He go walking in the mountains. He's always trying to get access to maps and so on. And for me, that's the difference. He's able to mentalize that very well. Okay.
Sorry, about the previous slide, did you also have the chance to compare gender? Because there's this legend saying that guys in women don't have the same.
No, we don't have. We were talking about that many times, and the referees they asked about that. Yeah. We don't have enough subjects to ask this question, and yeah, I'm not sure how to deal with that.
Is it a legend, or is it
I don't know. Maybe Malika does know more than me about that because I never went through that, and I'm not confident with that.
To answer, it's not a legend that the men are better than women by average. Okay. However, the interval is far greater than the mean. So let's say that men are here, but it spreads from here to here, and women are here, and it spreads from here to here. Right. So if you just take the average, it's a little above, but the dispersion is very, very wide. So maybe you can say that 5% of men are better than women, or you see?
Yeah. Do you think it's related to cognitive processes, or it's just, as I said, for blind people, it's just
I 100%
education?
That it's education.
Yeah.
And it's exactly why women are also a little better with verbal acquisition. Because most young parents ask their daughter how their day went and go and play outside with their son. So it's not weird that women develop more verbal acquisition and men spatial performance. So
it's the same story. You have to play with maps to get good at maps.
Of course.
Yeah. I can stop here. If it's okay for you. The rest is another story with providing the teachers with tools to make their own maps and so on. So we use Arduino, Raspberries, and so on. So they can design their own tools.
I can hope to see.
I'll show you. Private presentation. Thank you very much.